All right, we're going to go ahead and get started. I'd first like to welcome everyone. Thank you for attending Poseidon Systems' first webinar. This is an introduction to metallic debris monitoring. Our topics today are going to cover the basics of metallic debris monitoring, so what it is, how the technology works, how it compares to particle counting, what is the installation process, what is the data that it outputs, and then how we interpret that, and how it could potentially save you or your company money. To avoid any unattended background noise, we have muted the attendees, but we do encourage you guys to ask questions throughout, so please use the question section on your control panel, and we will have a designated Q&A section at the end of our webinar. Our speaker today is Ryan Brewer. He is the Vice President of Poseidon Systems. He has 10 plus years of experience in the development of fluid diagnostics. He earned his bachelor's from Penn State and his master's from RIT. So I'll hand it off to Ryan.
Thanks, Madison. And thanks to everybody who decided to join us today. This is, as Madison mentioned, our first webinar, and we'll be conducting these on a regular basis going forward. If you have suggestions for potential topics or areas that you'd like to see explored in more detail, please send us those suggestions so that we can take those into account and build those into future webinar programs. Most everyone who's on the call today is familiar with Poseidon Systems, but there's a few who are not familiar with us. So I just want to spend a few minutes going over who Poseidon is and what we do. So Poseidon is a leading innovator in the field of fluid diagnostics. We were established about 5 years ago, born out of a larger condition monitoring company that specialized in everything from vibration monitoring to electronics prognostics. Poseidon was stood up to focus solely on the commercialization of fluid diagnostic sensing technologies, and since that time our capabilities have grown to include online wear debris monitoring, online oil condition monitoring, viscosity sensing, water and oil monitoring, custom monitoring systems, offline ferrous metal in oil measurement systems, and we have a series of custom monitoring solutions and data acquisition systems to support these types of equipment as well. So the slide up now shows a few of our sensors. On the left-hand side, we start with metallic debris monitoring products. The top two images are our Trident DM products, and those are the products that we'll be discussing today in more detail. The bottom left product is our Midas product, which is the offline benchtop ferrous metal in oil detection system. In the middle we have oil quality products. We make a electrochemical based measurement system for monitoring the properties of oil and detecting contaminations and breakdown of oil. And those are the top two sensors shown there. We also have water and oil sensors and viscosity sensors that I mentioned previously. Our data logger products are used to collect information from our sensors and post information and push that information to where our customers want to use it and view it. So the data loggers are often used as part of custom monitoring systems, which are shown in the bottom right, which typically include several different sensors. They may include a debris sensor and an oil condition sensor, or oil and water, or oil and particle counting and water. So we use different variations there to try to meet our customers' specific needs. All right, our first topic today is what is metallic debris monitoring, and perhaps just importantly, what isn't it? So we'll start off with a simple definition: metallic debris monitoring. And maybe an important note, it's not just metallic debris monitoring. It's often called debris monitoring, wear debris monitoring, in some cases particle counting, particle monitoring. There's a large number of different names that this sensing technology takes, but here's the basics, or at least the basics of the technology we're talking about today. It's a device which utilizes inductive coil sensing technology to detect metal particles in a fluid stream and reports the particle counts, particle size, and particle type to the user. The technology is typically used to assess the health of a piece of rotating equipment, such as a gearbox. The specific product we'll be talking about from Poseidon's perspective is our line of Trident DM sensors. These sensors offer the best-in-class particle sensitivity. We can sense down to a 40 micron ferrous particle in a 12 millimeter fluid bore. Using that 12 millimeter fluid bore, we can achieve flow rates of about half a liter per minute up to 40 liters per minute. The outputs of this sensor cover a wide range. We can output particles by size and type in a series of size ranges known as bins. For example, 0 to 100 micron, 100 to 200 micron, so on and so forth. We can output an estimate of ferrous and non-ferrous concentration, the amount of mass of wear debris that we're seeing per unit volume of fluid. We can also output flow rate estimates as well as cumulative mass estimates. A primary communication interface is RS-45 and RS-232 using a Modbus RTU protocol. This is a fairly standard industrial protocol that is easy to connect to an existing host system. We'll talk more about that later on. So let's launch into some of the benefits and capabilities of wear debris monitoring. First off, and probably most importantly, a metallic wear debris monitor can detect metallic wear debris. No surprises there. We can monitor the wear levels over time and use that information to determine asset health. Secondly, the technology is a real-time sensing technology. As soon as a particle passes through the sensing bore, it's counted by the sensor, and that information is available to be read by a host system. So we detect wear when it occurs, and that information can be used to identify the root cause of the problem. Third, it's a continuous monitoring technology. So in addition to being real-time, the continuous coverage allows you to detect events that can't reliably be captured by periodic analysis or inspection. This is particularly important for wear debris monitoring, as wear is not a continuous, easily trendable process. It starts and stops and accelerates and decelerates depending on the operating loads and other conditions that are present within the system or the type of the fault that's present. Wear debris data is easy to interpret. In contrast to other condition monitoring technologies, there's really no expert required. And the primary reason for this is we are not an inferred measurement. We're a direct measurement of the fault you're trying to observe. We're actually detecting metal particles as they're being shed by a crack or a pit or by misalignment or other types of failure modes. Whereas other types of sensing technologies are measuring a secondary result, increase in temperature or the vibration that stems from this metal that's being generated. Fifth, we reduce maintenance costs. Early fault detection can reduce secondary damage, and it can also lead to lower cost of corrective actions. Now, there's a number of other ways that wear debris can save you money, and we'll discuss those later on in the presentation. Sixth, the technology can reduce downtime. And this is true of any condition monitoring technology, but being able to detect a problem early allows you to plan your maintenance activities accordingly. Early planning, in the case of a gearbox problem, for example, can reduce downtime from several days to do a gearbox repair down to just 1 or 2 days to do a gearbox repair or replacement. And the last item we're going to mention here is we can increase the useful life of the assets for monitoring. And the reason we can do this is wear debris is actually a good tool to use for fault severity assessment. And by trending that fault severity over time, you can determine how close you are to reaching catastrophic failure and actually optimize your equipment changeout. And every additional day that you can get out of a piece of equipment is money saved in the long run. Now we're going to do a quick comparison of wear debris monitoring versus some of the other condition monitoring technologies out there. We're going to compare on the basis of early fault detection here, and wear debris really stands out in terms of early fault detection. And that's for the reason I already mentioned. We're detecting the metal as it's being generated by the fault, and it's the earliest sign in many cases of a potential problem. So before a pit starts to open up, that can't be detected by any other mechanism than by wear debris monitoring. And as that pit starts to open, metal is generated, detected by the wear debris sensor. As the pit grows, then it begins to become detectable by something like vibration analysis. And then as the fault severity increases, some of the other monitoring technologies listed here can then detect that fault. Looking on the right-hand side, I kind of listed some of the advantages and disadvantages of each method. In terms of wear debris monitoring, wear debris has excellent fault detection, but limited fault isolation capability. And fault isolation is really the primary advantage of vibration analysis. It performs very well in terms of fault isolation, has pretty good fault detection, but the primary weakness of vibration analysis is in planetary systems. And that's largely due to the complexity of a planetary system in combination with the slow operating speeds and variable operating speeds that are common in a planetary type gearbox. Being able to interpret or detect useful vibration features from a complex gearbox can be more challenging. Moving up to prognostic models and data mining, these are really, their capabilities are highly dependent on the inputs you have available. If they're using vibration analysis and wear debris monitoring as inputs, they can be quite useful. If they're based on the existing SCADA data, then it's all dependent on what type of sensors are available on the SCADA network to make predictions from. Temperature monitoring, as most of us are familiar with, it only provides late-stage detection, wear-out conditions, really providing limited early warning. And oil sample analysis, I only included on here, though it's not a real condition monitoring technology. It's often cited as a technology or capability people use to detect a system problem. But in our analysis of people's oil analysis results, we really find little correlation with actual asset health. So moving on to how the technology works. So as I mentioned earlier, the technology is an inductive coil sensing technology. That means one or more windings are wrapped around a non-conductive sensing bore, and those windings are then energized by high-frequency oscillating voltage. The use of a high-frequency oscillating voltage in combination with the coil creates a magnetic field that is parallel to the sensing bore, and the field lines I illustrated there in the top right. As a particle travels through that field, it couples with that magnetic field, causing a measurable change in the electrical properties of the sensing coil. And we're measuring that as a change in impedance in terms of real and imaginary impedance. Interpreting that signal that we get out, and an example is shown there on the bottom of the real and imaginary impedance changes that we're measuring. That can be interpreted with the magnitude of the resulting pulse as a particle passes through being equal to the particle size, the duration of the pulse being equal to the speed at which that particle is traveling through, and the relative phase angle between the two channels, with this one being positive and this channel being negative, indicating whether it is a ferrous or non-ferrous particle. So the advantage of this inductive coil sensing technology is it can really see quite a small particle. In the case of Poseidon's technology, we can see down to a 40 micron particle. And the figures that are illustrated here are just to give an idea of how small a 40 micron particle really is. It's approximately half the width of a human hair that we can detect to, or in the range of a piece of grass pollen. This is really quite impressive, and as we increase the bore diameter, we lose sensitivity, and some of the products on the market are only capable of reading about 350 to 400 microns and larger, which would be represented in the last figure there, the size of a dot of an I in a typical newspaper. So we're often asked, why would you want to monitor particles less than 100 microns? We've been told that anything under 200 microns is normal wear and we shouldn't worry about it. Well, from our perspective, there really is no such thing as normal wear. All machines have some level of wear, that's true, but any machine that has wear eventually fails. So understanding what your wear is, whether it's considered in the normal levels of sizes or abnormal levels of sizes, is important. Even small particles in the 10 to 20 micron range can cause metal-to-metal contact, leading to secondary damage in a system. By monitoring these trends in small particles, we understand what normal is so that we can better define what abnormal is. It's like having a temperature sensor that can only read 100 degrees C and above. If 100 degrees C is your alarm limit, well, then you have a nice binary sensor, but it would be nice to be able to see how close you are to that alarm limit and not just have a binary switch. So the trends in small particles can be more reliable in actually some failure modes. I'll provide an example of that later on in the presentation, an example where we only observe sub-200 micron particles, but there is clearly a fault within the system. And in many cases, they're the first sign of a problem, especially in wear-out conditions. You see small particles before you see large particles. So moving on to our next topic, how does metallic debris monitoring compare to particle counting? And this is a question we get quite often, or folks stating that they're going to install a particle counter to monitor the health of their asset. I just want to explain a little bit about the differences. We're going to jump back to our definition again. In terms of metallic debris monitor, there's three key phrases in this definition we need to pull out. One, it's an inductive coil technology. The second, we're looking at metallic particles, with the emphasis being on the word metallic. And thirdly, we're monitoring the asset health. Moving on to a particle counter, the technology these sensors employ is based on light scattering. That there's a laser or other light source that's shown through the sensing window and detected by a photodetector, and that's detecting particles of any type, and that's a key differentiator there. Any type of particle versus metallic particles only, and the technology is most often used to monitor oil cleanliness rather than asset health. Here's a visual comparison of the two, the inductive coil technology that I already discussed, shown on the left, and the optical detector shown on the right. The laser passes through as a particle interrupts that beam of laser light. It creates a scatter pattern that is picked up by a photosensor, and the degree of that scatter correlates to particle size and or particle concentration. Just a quick comparison of the features of an optical sensor versus an inductive coil sensor. Application we already mentioned. The application for optical is it's better suited for oil cleanliness monitoring. Inductive coil, better suited for asset health monitoring. Flow rates, opticals use very small openings to support the visual chamber. Typically they can only support a few milliliters per minute of fluid. And with inductive coil, the Poseidon sensor with a 12 millimeter fluid bore, we can support up to 40 liters per minute. In terms of particle size range, optical is looking at things that are very small. sometimes down to a single micron, up to about 21 microns. And the results are typically reported in ISO cleanliness codes. And due to the limited window size, larger particles are actually filtered out or blocked from detection altogether. And as I mentioned earlier, the inductive coil sensor is looking at particles in the range of 40 microns and larger. A couple others I'll hit quickly. Particle discrimination, none on the optical side, so you're looking at not just metal, you're looking at sand, dirt, dust, air bubbles, water bubbles, and others. And in terms of temperature range, the inductive coil is a completely non-obtrusive device. The windings are outside of the actual fluid flow, so there's no electronics inside the heated oil, so we can actually operate at temperatures above 100 degrees C. In comparison to online optical particle counters, offline sensors or offline oil analysis has some of the same limitations. So offline particle counting uses typically the same laser light scattering type approach. So it's limited by the presence of nonmetallics, air bubbles, water bubbles. You'll see a general increase in particle counts with oil age, which makes extracting asset health information more difficult. And you often have inconsistent wear generation rates in an asset, so the periodic sampling of an offline analysis makes determining health even more difficult. In terms of iron concentration values via something like an ICP test, the particles seen by this type of test are typically 3 microns and smaller. Accordingly, these particles are never really filtered out. They continuously circulate through the system and continuously increase over time as the oil ages. So for the same reason I mentioned before, as this trend is continually increasing, it's difficult to determine a threshold to define what is healthy and what is not healthy. That said, offline analysis is certainly a valuable tool. It just needs to be used for the right purposes. It needs to be used to monitor the age of the oil, the health of the oil, and make sure the oil is performing its lubricating function properly. Without this, we'll certainly see increases in wear rates, but it is very difficult to determine if elevated wear levels are occurring from just a simple offline oil analysis. This is a topic we're going to cover in detail in next month's webinar. So the next topic we'll cover is how are these things installed. First off, we'll talk about data connectivity. There's two sides to the coin here, mechanical integration and data connectivity. In terms of data connectivity, we can connect our sensor to a data acquisition device, direct to a cellular network, and push data back to Poseidon Live. Alternatively, we can connect to an existing host system, such as the SCADA network, which is shown in the bottom half. So our sensor to a host, and that can be Poseidon's own data logger. It can be a controller or PLC. It can be a vibration-based condition monitoring system. We've done integrations with several vibration system providers. From there, it connects to the turbine network and is typically acquired by a historian, such as a PI historian. And if the customer is interested in having Poseidon support with data analysis and interpretation, that data is then sent to us most often by FTP, and we do analysis using our Poseidon Live software. On the mechanical integration side, there's 3 primary installation locations for a metallic debris monitor. First, the inline mainline filtration loop, and in our gearbox cartoon we've got oil being pulled from the sump, pump, mainline filter, returned back to the gearbox. Inline secondary filtration would be a secondary fine filtration system, and we have a device compatible with the CC Jensen filtration system for this type of installation case. Sensor mounts between the pump and filter, and oil is returned back to the gearbox. Third would be a bleed flow configuration, where we pull typically from a sample port through our sensor and return back to the top of the gearbox. Poseidon supports the second two installation configurations, the inline secondary filtration and the mainline bleed flow configuration. The reason we only support these two is we believe that particle sensitivity is critical in accurately determining asset health, and we are unable to achieve a high enough sensitivity with a mainline configuration for many applications. So just to briefly explain why we made this decision, the example here shows the metallic debris monitoring counts resulting from a wind turbine that had a high-speed intermediate shaft cracked bearing. The plot on the left shows the wear debris concentration versus time, and we can see it bouncing along at normal levels before having a trendable uptick in wear rates, which caused the customer to shut down borescope and identify the problem. If we actually look at the number of counts that were observed, the total number of counts observed during this time period, in the 50 to 100 micron range, we observed 117,000 particles, and 100 to 238,000. But in the larger particle sizes, we saw virtually no particles being generated by this particular fault. In terms of percentages, 99.9% of everything we observed was sub 200 micron. And in terms of total mass, approximately 97% of everything we observed was sub 200 microns. So this is the reason we elected to support the small bore sensors and not the large bore sensors with our product line. I'll show a couple quick pictures here illustrating how a typical installation is performed. These pictures are from a wind turbine application. First step would be mounting the sensor to a backplane. In this case, it was mounted to the backplane of a filtration system. And the tees and fittings and hoses are connected to the sensor. The supply and return lines are also teed in. The top shows a picture of the return line being teed back into the gearbox, and the bottom picture shows the sample port being teed in. For data connectivity, there's a single cable that runs from the sensor, in this case back to the top box in the wind turbine nacelle, and connects into the host system. In this case, we're using our AP2200 data acquisition and cellular connection device, and we see the single cable coming up in and connecting into that device. We also have power being routed into the data acquisition device, and this device controls power to the sensor as well. A similar configuration would be used if we were connecting into an existing PLC or condition monitoring system. We'd have a single cable running back from our sensor and connecting into the condition monitoring system, controller, or other host with power being teed into that cable. Next topic is, how do we interpret wear debris data? The first recommendation I'm going to give is don't set limits based on counts alone. Counts alone can be extremely misleading. Some customers have used counts in the past and set thresholds based on if we observe over 5,000 counts or 10,000 counts, whatever the number may be, then we have a problem. Well, the primary issue is if you're not taking into account the particle size and in turn the particle mass, you can really be missing the big picture in terms of the amount of wear actually present. So we need to look at our wear rates versus time, and we need to look at the amount of mass that has been generated. The comment here on the bottom left, a single 800 micron particle represents more material loss than 500 100 micron particles. This is an important thing to keep in mind when we consider using total particle counts as a condemning limit. So when Poseidon does an analysis, we look at particle distribution, we look at mass versus time or concentration, and we look at the cumulative mass and interpret that as a fault size. Here's an example. This is an example from a wind farm. We're monitoring 20 wind turbines here, and this plot shows histograms for each of the 20 turbines showing the particle counts observed. And as we can see, the colors are 40 to 100 micron, 100 to 200, 200 to 300, 300 to 400, and greater than 400 microns. Quickly looking at this, we see a few standouts. T9 and T10, these are generating wear and significant amounts of wear across the entire spectrum of particle size ranges. Additionally, we see T18 and T3 generating a high number of very small particle counts. Second thing we do is interpret this into cumulative mass or fault size. So we take those particle counts, multiply them through by the particle masses for the given size ranges, and come up with a mass estimation. So for this particular site, we were seeing mass loss rates of about 5 grams per month on T9 and 1 gram per month on T10. So these are pretty significant mass loss rates, especially since we're observing approximately 1/10 the total flow rate in the system. So total mass loss is closer to 50 grams. So we take these cumulative mass levels and interpret them not just in mass versus time, but in terms of how large of a fault that would represent before making a decision as to whether additional analysis or inspection should occur. The last thing we look at is concentration, and in this case we're looking at a 24-hour average of concentration, and concentration being the amount of ferrous material generated in a 24-hour period divided by the total flow observed in a 24-hour period. These types of plots result in some interesting analysis, and this is a case here that we had a fault that we were detecting. We see an increasing trend in the concentration levels that breaches our warning limits and then eventually breaches our alarm limits. So what's more interesting is taking a look at this a little bit closer, and we can see here this is power output from the turbine. As the power drops to zero in a shutdown event, we see a spike resulting in elevated wear generation. And looking at it at a smaller time basis, a 10-minute average down below, we can see that sure enough, pretty much all of this wear represented by the spike above occurred all at the same time as a result of that shutdown event. So this is how we can get some additional value out of wear debris data, not just determining is my asset healthy or not healthy, but we can start looking at what conditions are leading to wear and what conditions are causing us to have premature gearbox failures. Now I'll address a couple slides showing examples of fault detections. In this example, this is an incipient event. This particular turbine bounced happily along well below our thresholds for many months, and then we saw a spike around Valentine's Day where we breached our alarm limits. And when we took a closer look at this, we saw not only did we breach our alarm limits in terms of ferrous wear generation, but we also were generating significant non-ferrous wear as a result of that initial event. And looking at the non-ferrous plot below, we can see that non-ferrous wear spikes at the same time and continues on for several months afterward. This eventually tapered off in non-ferrous wear generation, but this is a good indicator that this was the beginning of a bearing failure, with initial ferrous wear and non-ferrous wear stemming from the bearing material itself as well as the bearing cage. This turbine has been added to a watch list for borescope inspection. The example shown here, we actually installed across an entire wind farm. Shortly after we installed, we identified 3 wind turbines, all 3 of which had faults. We notified the sites that we had identified 3 problem turbines, and they performed an initial round of borescope inspections on these turbines. The results of these borescope inspections were no damage found. Fast forward about 3 to 6 months, and they performed a round of preventative maintenances on the site. During the PMs, they identified a significant amount of metallic debris in one of the filter canisters. This initiated a second round of borescope inspections. And in this second round, all 3 turbines faults were identified in, and the severity of the faults that were detected correlated with the levels of wear debris that we were seeing in our sensor data. All 3 of these required gearbox replacements, as they were planetary stage faults on a make and model gearbox that required replacement rather than repair. Through continuous monitoring, we were able to get about an additional year to year and a half of life out of these gearboxes, and all 3 were changed at the same time during low wind seasons. So that brings up one of our last topics. How does metallic debris monitoring save us money? First off, we'll talk about cost avoidance. In terms of gearbox replacement versus repair, particularly in the wind industry, we're looking at about $250,000 to replace a gearbox versus about $30,000 to repair. This is all dependent on the type and nature of the fault, but if you're able to save one gearbox and do a repair versus replacement, you're looking at a cost savings of about $200,000. In terms of cost optimization, the example I gave earlier is a good example. In that particular site, they had 3 turbines that they needed gearbox replacements. They were able to limp the 3 along until they were able to get them into low wind seasons and change all 3 gearboxes at the same time rather than waiting for a failure. So this resulted in savings 2 ways. One, the downtime on each tower was only 1 to 3 days for the gearbox replacement versus about 40 days for an unscheduled maintenance. Secondarily, in terms of cranes, we only called 1 crane out at about $90,000 versus 3 separate crane call-outs at $270,000. Cost optimization continued. Early warning and continuous monitoring through wear debris. Through early warning of faults, we can minimize the cost of lost availability, as I mentioned, by allowing the maintainers to schedule maintenance to occur during low wind seasons or during curtailments. Secondarily, we can provide improved fault severity assessment versus other condition monitoring technologies. And you can use that severity assessment to extend the life of the gearbox and make sure you're changing it at the right time. This slide just briefly summarizes where the savings can come from. The pie chart there isn't really representative of how much savings can be afforded. That's all dependent on the circumstances and the type of fault, the type of asset, whether you're under warranty or not under warranty. All right, I'm getting the nod from Madison that we've reached our time limit and are going to take a few questions now. And she's compiled a list of questions for us.
Thank you, everyone, for submitting some questions throughout the webinar. The first question for you, Ryan, is how long does it take to install these sensors in general?
Okay. So installation is dependent on the type of equipment that we're talking about. Most of our installations are in the wind industry, and for a wind turbine, not including the climb time, up tower time for 2 technicians is about half an hour to perform the mechanical installation, cable routing, and initial data connectivity checks.
Okay. Next question is, what are the dimensions of your sensors?
So the most important dimension to consider when integrating the sensor into your system is actually the fluid bore diameter. So we have a 12 millimeter fluid bore diameter that I mentioned, supporting up to 40 liters per minute. So you need to make sure the application is suitable for that flow rate, and if not, find the correct installation configuration in terms of plumbing to support that flow rate. And for overall physical dimensions, the sensor is approximately 6 inches long, 4 inches wide, and 4 inches high.
And next question is, how fast could you potentially deploy 100 units for a wind farm?
So that's a question we get quite often as well, how fast we can roll out. We're able to manufacture, I guess, faster than a typical wind farm could deploy. So when we go to a wind farm, we typically work with the site to align our installations with their PM schedules. And that allows them to minimize their downtime. In a typical PM scenario, you're doing 2 to 4 towers a day, and we're able to deliver about 10 to 20 sensors per day. So we're able to keep up with the installation rates so that there's no delays or long lead times to actually getting equipment and getting it deployed.
Next question is, do you install the sensors or do you offer some sort of installation service?
So that can go both ways. What's typically done is we arrive on site and assist with the first, say, 1 to 5 deployments and train teams of technicians on the deployment. From that point forward, the site is free to do the installations on their own accord according to their PM schedule to avoid any unnecessary downtime or distractions. Alternatively, depending on the size of the site, we'll either deploy our own resources to deploy across the site, or we have agreements with a number of third-party operations and maintenance companies that will perform the deployments for us.
We're going to answer a couple more questions. The next one is, does your sensors work in high temperature environments?
So one of the advantages of the technology that I mentioned, of inductive coil sensing technology versus particle monitoring, is that we're actually non-obtrusive. So the oil can be quite hot, and the sensor can survive in those applications. We've done applications up to about 130 to 150 degrees Celsius.
Okay, and we're going to go through 2 more questions. One was, you mentioned something about Poseidon Live. How do you access or use that?
Sure. So Poseidon Live is a development we've been working on over the last several years as a data portal and analysis tool for viewing the results, or viewing the data collected by the sensors, wear debris sensors, oil condition sensors, and even some SCADA information. Is all collected and presented there on Poseidon Live. Using the tools on Poseidon Live, you can set alarms and perform measurements and analysis, export data for additional analysis as well. We'll work with our customers that are using our sensors to set up private accounts for them in which they can use that tool. This will be something we address in a future webinar as well, where we go over Poseidon Live, its features and capabilities. That will be in about 2 months.
So the last question that we'll review today, which kind of goes nicely with that, is what threshold would you recommend setting up for alarm notifications?
That's a good question. So this is dependent on what we're monitoring. So I'll start with wind. In the wind case, what we do is we analyze a population of wind turbines of similar make model type and look at it in terms of the statistics. And if we're seeing an average concentration level and we calculate the concentration and standard deviations. And from that, we can determine warning and alarm limits. And we typically set our warning limits at the average concentration plus 2 standard deviations, and we set an alarm limit at the average concentration plus 3 standard deviations. It's important to have a good representative population spanning not just healthy turbines, but healthy and unhealthy. And outliers are removed from that as well, so the limits aren't skewed to be too conservative or too high. In other applications, we would take a similar approach, but we may need to rely, if we don't have a large enough population to pull from, on the data from that individual asset. In that case, we're going to be looking at rates of change over time. So we'll, again, set a statistical limit based on that particular asset of what normal appears to be, and then set a mean plus 2 sigma, mean plus 3 sigma type limit. Those alarms are also set not just on concentration, but we look at it in terms of mass loss over, say, a one month operating time period, so a longer time interval. And we'll also look at it in terms of what the fault size is, and this can be important for some types of assets that are smaller in nature, to set it based on fault size versus setting it on total mass loss in a given time period.
So we have time for one more question that we just got in. Then any other questions we will answer via email. Does this sensor cause a pressure drop?
So in terms of pressure drop, I guess anything in a lubrication system technically causes a pressure drop. Even if you were to extend the length of hose by a foot, there is a pressure drop associated with that. But as long as that hose diameter is consistent with the rest of the hose in the system, it's a minuscule pressure drop. So, for example, our sensor that is installed on the CC Jensen pump and filtration system, the bore diameter of that sensor matches the bore diameter of that filtration system. So the pressure drop we're seeing there is negligible, especially considering the flow rates are so low in that application, around 1 to 2 liters per minute. As you get up to higher pressures or higher flow rates, the pressure drop can become more significant in the range of a couple psi, depending on the flow rate and viscosity. If that's a concern for your application, feel free to follow up with us with information on your lubrication system and the type of oil you're running, and we can give you some calculations on what the pressure drop would be in the system.
Great, thanks for answering those questions, Ryan. We do have a few unanswered that we were unable to get to, so following the webinar, we will send those answers out to those questions via email. Or if you think of questions after the webinar, we will have a contact slide up shortly in just a few minutes and get that going for you. So our next webinar is going to be held next month, and it will we covered it briefly today, and it will go more in depth on the offline versus online oil analysis. So we hope to see you at that one, and again, that's on May 27th. So this is the contact information for any additional questions, or if you'd like to reach out with us about anything regarding the webinar or our company in general, reach out to Ryan Brewer. I also just want to mention briefly that we will be giving out the online recording. It will be available through our website at PoseidonSYSsystems.com, and it's going to be under the video archive section. We'll also probably be sending it out via email after the webinar as well. And if you want to stay up to date with our webinar schedule, we will be posting that shortly on our website under the webinar section, so you can see in the upcoming months what topics we will be covering and when you can join those. So again, just wanted to thank you for attending our webinar today. Hope you guys enjoyed and found it very informative. and thank Brian again, and we will hear from you guys shortly. Thank you.